Hello, Gregory Carlson here with the Calculus Building. Let's look at a few examples of finding some higher order derivatives. I think you're going to find it's pretty simple. Here I've got a function, y equals negative 9x to the 8 minus 5, and they want us to find the second derivative of it. You can tell by the 2's that we have right here. And so basically that just means find the derivative twice. So let's first find dy dx. So the derivative of this is you use the power rule, so that'll be negative 72x to the 7. If that was confusing for you, you should review the power rule video. And the derivative of negative 5 is just nothing. It just goes away. So now we're going to find the second derivative. And totally ignore this. Totally ignore this. We don't need to look at this anymore. Now we're just, it's like we have a new function, a new equation, and now we're just going to find the derivative of this new equation. And so we just do the power rule again. So 72 times 7 equals 504. So this is negative 504x to the 6. So that was pretty simple calculation to make. But I want you to think about just the power of what we just did. Here's a function of degree 8, okay, that has 8, roots. And we just found how fast its change is changing. So we just found out how fast the change of the curve is changing. We just some simple steps. That's just amazing to me. Let's do another one. Here we have y equals 7x to the 4 over 4 minus 2x. So let's find the derivative. So first let's find dy dx. So I have x to the 4, and remember that the 7 over 4 we can treat as like a constant. So let's pull it to the side and multiply that by 4x to the 3, which is the derivative of x to the 4. And then this would be minus 2, because the derivative of negative 2x is negative 2. Alrighty then, so that 4 is going to cancel with the 4, so just to simplify that a bit, that's going to be 7x to the 3 minus 2. And so I didn't take the derivative there, I just simplified. So now we're going to find the second derivative. So d squared, it's not really squared, d to the 2y dx to the 2. So second derivative, we see that we're going to get 21x squared, and the negative 2 goes away. So there is your second derivative. Again, we have this function, and we just found how fast the change is changing. All right, let's do this last one. We're finding the second derivative of this, and I have a bad feeling about all of this material. Remember that little rule we came up with up here? I have a feeling that it might be a waste of time to find these derivatives. Let's see if I'm right. dv dt is equal to, for our first derivative, it would be 6t plus 8. And dv over dt 2, our second derivative, would just be 6. So you can see the second derivative of this quadratic is only going to be, the only thing that's going to survive is this first term. And that's a really interesting thing I want to show you. You may remember that back in college algebra, we gave you a formula for gravity. And we said if we're in meters per second, the velocity, well, let me just write the formula down first. You may hopefully remember this formula. If we gave you the feet version, it looks like this. So if you throw an object up into the air with initial velocity of v up into the air and initial height of h, this is the gravity equation. Ignoring air resistance, it goes, because of how big Earth is and how much mass it has, we have gravity of an object going straight up and straight down. That's defined by these equations. So let's take the derivative. Let's find f prime of x. We get negative 9.8 t plus v naught plus h. So at any given moment, that's going to be the speed of the object. And look at the second derivative. Oops, I'm sorry, that h shouldn't have been there. That h would have gone away. So the first derivative would be that right there. And then we take the second derivative. All that we have left is negative 9.8. Think about that for a second. That's the acceleration due to gravity. So that's why we use 4.9 or negative 16 in the equation, because the acceleration to gravity is 9.8 meters per second squared in the down direction, or it's negative 32 meters per second squared if you're talking about a feet per second squared, if you're talking about feet in seconds. And so I hope you see that we can now describe gravity with this second derivative, because that constant is the constant acceleration of gravity. And that's why if you drop two objects of different masses, and they'll pretty much hit the ground at the same time, because they're both being acted upon by the same acceleration. Now, by the way, why is it meters per second squared? That's kind of weird. How do you square time? What a weird concept. It's better to think about it as meters per second per second. Okay, that's the better way of thinking about it, because velocity is meters per second. That's how fast you're going. And so how much that's changing? Well, you're going to be changing, like say you're accelerating, you're going to be gaining 3 meters per second per second. You see, so it's meters per second describes an acceleration because your velocity is changing each second. So I know that was a kind of a little tangent we just went on, but I just wanted to show you the application to the second derivative and how gravity acts on all objects around the Earth. And if the Earth was bigger or smaller, the only thing that would change are those two numbers. Let's see, it looks like I have time for a few more examples. We'll probably go to part 2 with this stuff. Okay, so we got y equals the 5th root of x, and we want to find the second derivative. So let's find the first derivative first. Before I do that, let's remember that we could rewrite this as y equals x to the 1/5 power. Is that okay? The 5th root of x is the same as x to the 5th. So the first derivative of this would equal 1/5 x to the 1/5 minus 1. Okay, so that would be the first derivative, and that would equal 1/5 x. Okay, a 5th minus 1, that's 5/5, so that would be negative 4/5. So is that okay for my first derivative? 1/5 x to the negative 4/5. So now we ignore everything previously, and we're only looking at this. So let's take the second derivative. So power rule, I bring this down and multiply. So negative 4/25 x to the negative 4/5 minus 1. Is that okay? And so that's going to equal negative 4/25. Again, that's 5/5, so it's going to be x to the negative 9/5. And that's the second derivative. So we've come a long way since Nero's stop sign, don't you think? We've come quite a long way, and I think I have time for another example, so let's do the next one. Remember back when we were trying to figure out if Nero had stopped at that stop sign, and now we're finding second-order derivatives. All right, so I see that I have an x to the 3 in the bottom here, so let's go ahead and find, this should say f of x is equal to this. Find the second derivative. I'll fix that in your notes. Find the second derivative if f of x equals that. So the first derivative is going to equal 10x minus 14. Okay, so what would this equal? So first off, we have negative 6 is kind of like a constant, so let's pull that off. Remember, this would be like x to the negative 3. So we would multiply by negative 3, and then it would be x to the negative 4, because we dropped that power by 1. So if that was confusing for you, you might want to review some of the earlier derivative videos or leave a comment for me in the comments. So let's clean that up. 10x minus 14 plus 18 over x to the 4. That's the derivative. So let's find the second derivative. So derivative of 10x is 10. The derivative of that is 0, so we'll just ignore it. The derivative of this, again, let's just write a plus, and we'll pull the 18 forward and take the derivative. This would be x to the negative 4. So it'll be times negative 4 x to the negative 5. So the second derivative would be 10 minus 18 times 4, which is 72. And then I'll go ahead and move that down. So notice that because if I have an x in the denominator, I can keep taking derivatives and derivatives and derivatives, and that power is just keep going to get bigger and bigger and bigger in the denominator. So that's one way we'll always have derivatives, is if you have an x in the denominator to start with. All right, I'm over 10 minutes, and so we'll finish up these examples in part 2 of this video. If you found this helpful, please like and subscribe and leave me a comment, and we'll wrap this up in the next one. See you there.